Let's look at a motion application with the LS Electric XGB PLC. For this example, we will be using a 3-axis motion system which utilizes many components offered at AutomationDirect.com. Our system is built on a sure-frame extruded aluminum base with casters. It utilizes IGUS dryland actuators and sure-motion couplers from Automation Direct attached to LS Electric gearboxes driven by L7P servo drives and motors. These drives are controlled by pulse train outputs from an XEM DN32HP 6-axis motion controller. We have attached a mounting plate and pen to allow us to trace the profile we will be working on today. Interpolated motion can be used to move in fairly simple 2-dimensional linear patterns, such as angular lines, or more complex 2- or even 3-dimensional patterns, such as a circular, helical, or 3-dimension linear profile. In this example, we will use a 2-axis linear interpolation to draw a triangle. We will be using the XPM IST indirect start function block for our move today. This function block is covered in more detail in the help topic on the indirect start and its uses in XG 5000. The function block uses the position data table in the XGPM software to predefine our linear interpolation. We have the XEM motion demo project file open in XG 5000, have connected with the XEM CPU, and are in monitor mode. This file is available to download from the XGB Interactive Guide at AutomationDirect.com. Let's open the Interpolation Routines structured text program and go to line 43 of the code. Here we find the trigger logic for the various interpolation routines. This program has been set up to use the user variable Motion Manager State as the index for a state machine. We are doing a linear interpolation, so we see that if the axes are ready and homed, and we make the run linear interpolation bit true, we will execute Motion Manager State 10. Starting with line 76 of the code, we see that motion states 10, 11, and 12 are all execution of direct start commands to position the 3 axes for the start of the linear interpolation. The z-axis in this case is positioned so that the pen is touching the paper, and the x and y axes are both positioned at 200 pulses. The final function in motion state 12 is to move to state 13, which is the actual execution of the linear interpolation. We see in state 13 that it will make axis 1 command dot linear interpolation move true. Let's run a search to find this bit elsewhere in the logic. We can right-click on the bit and go to Find Replace, Find Text. This opens the Find Replace pop-up window. Let's set the Look-In box to multiple windows, and then select Select All from the Find What drop-down window. It already put the variable name into the search box, and we can now click Find All. It doesn't appear that anything happened, but if we look at the information window in the lower right corner of the screen, we see that the Find One tab has automatically been selected. Let's expand that window upwards, and here we see the results of our search. We see that axis 1 command.linear interpolation move is used in 4 places. The first one is the spot in the interpolation routines program that we already looked at. The next 3 are all in axis 1 motion program, so let's take a look at them. We go to the project window on the left side of the screen, maximize the axis 1 motion program heading, and double-click on program. The first entry is on line 132. And we see that if this bit goes high, the PLC will copy a 10 into the variable indirect step number. If we now look at line 151, we see that a positive transition or rising edge one-shot instruction will activate the indirect start function block. We set the indirect step number to 10 earlier, so this is the line in the position data table for axis 1 that will be executed for a linear interpolation. Finally, we see that the bit will be reset once the indirect start done output goes high. This occurs as soon as the move is started, so it should not be used as an indicator of motion completion. To further dive into the details of step number 10, let's look at the position data table for axis 1 in XGPM. To open XGPM from the XG 5000 software, we go to Tools, Position Control. This will open the XGPM software. We can then open the XEM Motion Demo XGPM file. We will connect with the controller in XGPM as well. We have already configured axis 1 and axis 2 parameters in the help topic on initial motion configuration. Please refer to it for more details. To open the position data table, we will go to the project window on the left side of the screen and maximize number 1 axis data. We can then double-click on Position Data. This will open the one-axis position data table. We scroll down to line 10 and see that it is an absolute, linear, interpolated move, and the sub-axis for the move is set to axis 2. To properly understand the interpolated moves, it is necessary to view the position data tables for all axes we will use. Since the linear interpolation sub-axis is axis 2, let's open the axis 2 position data table as well. To see both position data tables at the same time, we go to Window, Tile Horizontally. This aligns the axis 2 position data above the axis 1 position data table. It is important to note that axis 1 is our x-axis and axis 2 is our y-axis. Looking at lines 10 through 12 of the axis 1 position data table, we see 3 absolute linear interpolation moves. The first 2 are single moves that continue to the next move, and the third in the sequence is a single move that ends upon completion. If we look at each of these moves, we see that axis 2 is selected as the sub-axis. In XGPM, when a particular line of the table calls out a sub-axis for the move, the corresponding line in the sub-axis position data table is what is executed as part of the interpolation. In our case, when we call line 10 of axis 1 position data table, the system will also execute line 10 of axis 2 position data table, since axis 2 is listed as the sub-axis for the axis 1 move. Since we are looking at lines 10 through 12 of axis 1, and each lists axis 2 as the sub-axis, let's look at lines 10 through 12 of the axis 2 position data table as well. We see that these 3 moves are all absolute single-axis moves. They do not need to be set as interpolated moves, since the main axis step calls out the control type of the sub-axis. Now that we've looked at the mechanics of how the multi-axis information is interpreted, let's look at the positions and velocities of the moves themselves. Remember that our program positions each of the axes at position 200 prior to triggering the indirect start for the interpolation. Line 10 will be an x-axis move to a position of 2500 and a y-axis move to a position of 1600. Line 11 will move the x-axis back to position 200 while the y-axis goes to 3200. And then the final move, line 12, will keep the x-axis at 200 and only move the y-axis back to 200. This will lead to the system ending exactly where it started. It is important to note that with interpolation, the system uses the sub-axis position, but ignores the sub-axis speed setting. Instead, it uses the parameter setting for interpolation speed and some advanced math functions to calculate the axis speed of each axis for this move. If we go to the parameter window, we can see this is set to synth. The documentation goes into detail on how it calculates these speeds, so please refer to it for more detail. We want a smooth profile that ends at the specified point simultaneously for both axes, so we will leave this setting at synth. Let's watch our motion system as we trigger a linear interpolation. We see the x and y axes start drawing. Then, when they reach the preset positions, automatically move to the second segment of the move. And finally end with just the y-axis moving the pen back to the starting point. Just what we expected. Perfect. We have now executed a series of linear interpolations to create a basic pattern. This system is very flexible and can have many sequential steps, so all sorts of interesting patterns and functions are possible with linear interpolation using the XGB PLC.